Hello, my name is Haolong Li. In this video, I will present our work done together with my supervisor Jörg Stückler, titled Online Calibration of a Single-Track Ground Vehicle Dynamics Model by Tight Fusion with Visual-Inertial Odometry. To achieve autonomous navigation of robots, we usually need accurate state estimation and knowledge of the motion model and the effect of the control inputs. Besides, we also want to have a model that can adapt to the environment change. For example, when we change the tire from high traction to lower traction. To achieve this, we propose the tight fusion of a single-track model with Visual-Inertial Odometry, and we call our method St-Vio. In St-Vio, we use the single-track model as a multi-step motion constraint, and we online optimize the motion model and the state estimation. And we use the motion model to perform forward prediction given control inputs. We base our method on a traditional VIO called Basalt, which estimates camera pose and velocity, as well as the 3D landmarks based on visual and IMU inputs. And we extend it by introducing new states, which are the extrinsic pose and model parameters, and by adding new factors, which are the dynamic model, geometry constraint, extrinsic pose random walk, and parameter priors. Let's have a closer look of the dynamics model. We use a single-track model for our robot, which is very often used because of its good balance between simplicity and accuracy. In this model, the front wheels and rear wheels are lumped together as shown in the picture, and it takes the throttle and steering as control inputs, and models lateral and longitudinal force to output relative pose and velocity. The parameters in this model include steering mapping, motor parameters, and tire coefficient. The lateral force is a function of the velocity, tire coefficient, steering, and steering mapping. And in this function, the velocity term appears in the denominator and leads to a singularity when the velocity is 0. And we introduce a soft thresholding function to make it singularity free. And additionally, we model the longitudinal force based on an empirical motor model, which takes velocity, throttle, and motor parameters as input. We tightly fuse this dynamics model with our VIO. And to do so, we need to have these two blocks, which are the windowed optimization block and the ODE integration block. In the ODE integration block, we use the ODE solver that takes the initial states and newly updated parameters as input and computes the multi-step predictions as well as the gradient with respect to the initial states and model parameters. And in the windowed optimization block, it minimizes the difference between the prediction from the model and the VIO estimates. And then it optimizes the states and the model parameters jointly and updates the model parameters again back to the ODE solver. To validate our method, we first evaluate the tracking accuracy with real-world data collected in different scenarios with different maneuvers, and compare the results, the RPE results, with the original VIO. And we can see in most sequences, our method can improve the tracking accuracy. We also evaluate the prediction accuracy. The orange bars denoted as online calib are the predictions using online calibrated parameters. The blue bars denoted as initial calib are the prediction using offline calibrated parameters based on sequence in a corridor scene. We can see that the online calibrated prediction has much better accuracy when the environment changes. This video shows the qualitative result of prediction of 100 steps in an outdoor scene with rubber tire. The VIO estimate is shown in green, the online calibrated prediction is in red, and the offline calibrated prediction is in blue. As we can see, that the online calibrated prediction aligns much better with the VO estimate than the prediction using offline calibrated parameters. To further show the effectiveness of our online calibration, we also performed experiments by changing to wheels with low tractions. Here is again the qualitative result by comparing the VO estimate with online calibrated prediction and offline calibrated prediction. To conclude, in this work, we present the tight fusion of a singularity-free single-track model with VIO. We perform online model calibration together with state estimation. By doing so, we can not only improve tracking accuracy, but also achieve online adaptation and motion prediction. And this enables the potential of our work for downstream tasks such as planning and control. If you want to learn more details about our method, please visit our webpage with the QR code.